Thank you all for standing by, and welcome to the first webinar of our fall series entitled Making Climate Change Data Relevant at a Local Level. These webinars are an initiative of the Ohio State University Climate Change Outreach Team, a multi-departmental effort within the university led by OSU Extension, Ohio Sea Grant, Bird Polar Research Center, and 6 other OSU departments to help localize the climate change issue for Ohioans and Great Lakes residents. I am Jill Gentis-Benicki from Ohio Sea Grant and Stone Laboratory, and joining me today is Dr. Dan Vyman. Dr. Vyman is an associate professor of atmospheric and oceanic sciences at the University of Wisconsin and is a Bryson Distinguished Professor of Climate, People, and the Environment. He conducts both fundamental and applied climate research. One focus area of his research includes assessing regional impacts of climate change. He serves as the co-chair of the Wisconsin Initiative on Climate Change Impacts Science Council, or WICCI, and the WICCI Climate Working Group. The WICCI Climate Working Group, funded by the Upper Midwest Great Lakes Landscape Conservation Cooperative, has recently developed a set of downscaled daily climate projections for the eastern United States. We're delighted to have Dr. Vyman here to discuss that downscaled research today. But before we do that, a few logistical issues as we get started. During our presentation, all participants will be in a listen-only mode. Afterwards, around 12:45, we'll conduct a question and answer session. If you would like to ask a question during the presentation, please feel free to use the chat feature located at your right-hand side of your screen, and I will collect and pose your questions out to Dr. Vyman at the end of his presentation. We have nearly 250 people on the webinar, a great diverse group representing governmental agencies, academia, and nonprofit groups from the Great Lakes and around the country. Please keep those questions coming throughout the presentation, and we should have a great Q&A session. As a reminder, this webinar is being recorded and will be posted onto our website for later viewing. Also, we will post a webinar survey in our chat feature toward the end of the hour. Please take a few minutes after the webinar to fill out that survey. It will help keep bringing you better webinars. So without any further delay, I would like to introduce Dr. Dan Vyman from the University of Wisconsin, who will present Making Climate Change Data Relevant at a Local Level. Dan, I'm going to unmute you. So you should be good, and I'm going to put on your presentation, and I'm going to give you the presentation ball. So
all right.
Have it.
All right. Thank you. And let me know if there's any issues with the audio as we're going through here.
You sound great.
Great. All right. Well, thank you very much, Jill, and thanks everyone for attending this webinar. This is a wonderful opportunity for us to let people know about this downscale data that we've just produced, and to let people know about some of the efforts that are going on here in Wisconsin at assessing climate change impacts in our state and our region. And I'll talk a little bit more about that as we go through the presentation. To begin with, I want to acknowledge some individuals and groups who have made this work possible. First of all, David Lorenz. David Lorenz is a colleague of mine here at the Center for Climatic Research and is the brains behind a lot of the downscaling and a lot of the efforts here. Has done a wonderful job in that creative, in developing a very creative methodology for addressing a lot of needs. The WICCI, the Wisconsin Initiative on Climate Change Impacts Climate Working Group, the number of individuals here who have helped out in producing this data, including the State Climatology Office here at Wisconsin. Of course, the Upper Midwest and Great Lakes Landscape Conservation Cooperative, who funded this part of the research, and we will be continuing to work with them to help develop an interface for interacting with this data in a more user-friendly way. Wisconsin Initiative on Climate Change Impacts, there are a number of scientists and individuals with whom I've interacted in WICCI who have informed the process here, and that interaction with people who are using the data has been fundamental to our our ability to produce a data set that's useful. And then the Wisconsin Focus on Energy program, who provided the first funding to develop the methodology. So the context of what I'm talking about today, I'm going to be talking about a recent downscaled data set of downscaled climate data that was produced in partnership with the Upper Midwest Great Lakes Landscape Conservation Cooperative. And the data set was developed for use in climate change impact assessment. And I'll explain a little bit about why this data, about how that was done. To begin with, so I'm a climate scientist at the University of Wisconsin here, and most of my talks begin with three things we know about climate change. And this is a bit of a review, probably for most people here, but I think it's a good context to set the stage for the rest of the talk as well. So, three things we know about global climate change. First, we know that carbon dioxide in the atmosphere is increasing, and we know that increase is anthropogenic in origin. So that means anthropogenic means we know that it's due to humans. And we know this from a variety of pieces of information, but probably the most solid evidence is looking at isotopic ratios of carbon and identifying a fossil fuel signature in them, as well as a signature of plants in those isotopic ratios. So that's one thing that we've known for a couple of decades now, that the increasing carbon dioxide levels in our atmosphere are due to human emissions. The second thing we know about climate change is that Earth's climate has been warming. In fact, it's warmed about 1.5 degrees Fahrenheit since 1900. I'll be switching between Fahrenheit and Celsius occasionally during the talk here. It's always, we present this material to scientists who are used to Celsius and people who are more used to Fahrenheit, so back and forth. So that'll, I'll try and express it in both Celsius and Fahrenheit when I can. We do know that global temperature has warmed by about 1.5 degrees Fahrenheit since 1900, and we can verify that using a whole slew of different pieces of evidence. We can take away urban heat island effects. We can look at biases and satellite estimates of temperature. We can look at upper atmospheric temperatures and surface temperatures. We can look at marine temperatures. And the changes that we have observed are robust. The third thing we know about climate change, or about greenhouse gases in our climate system, is that our Earth is warmer because of the presence of carbon dioxide and other greenhouse gases than it would be in the absence of those gases. So an example here, the greenhouse effect. If our Earth were warmed by the sun only, then the Earth receives some energy from the sun, and it warms up. And as it warms up, it starts emitting energy. And if there were no atmosphere, the Earth would warm up to the point where it were emitting as much energy as it's receiving from the sun. And at that point, Earth's temperature would be 255 Kelvin, or about minus 18 degrees Celsius. And even though I'm giving this seminar from Wisconsin, and minus 18 degrees Celsius sounds like a typical winter day around here, that's actually quite cold for the actual temperature on Earth, where we're much closer to like 10 or 15 degrees Celsius. So when you put an atmosphere on a planet, then as Earth emits radiation, a lot of that radiation gets absorbed by the atmosphere, and then the atmosphere then warms up and has to radiate energy away. The atmosphere, I would say the atmosphere doesn't know which direction up is, so it radiates both up and down. And so the Earth receives energy directly from the sun, but it also receives energy from the atmosphere. It's an additional source of energy that keeps our planet warm and keeps it habitable. And there's no controversy over the greenhouse effect. That's we're able to, why our planet is habitable. So these are three things that we absolutely know about climate change. Put this and a whole bunch of other evidence together, and the last IPCC report, the fourth assessment report, made the statement that most of the observed increase in global average temperatures since the mid-20th century is very likely, and very likely is has a specific meaning here, due to the observed increase in anthropogenic greenhouse gas concentrations. So very likely means there's a 9 out of 10 chance. They specifically define that. And I think that's important in the context of what we're talking about here, because it introduces the fact that our interpretation of information and what we do with information is probabilistic to a certain degree. And anytime we're making decisions, having information about the probability of various changes or effects provides information that we can use in making decisions. And that information is too often cast as uncertainty that we can't use, that prohibits us from making decisions. But in reality, most of the time that probability is actually very useful information. Okay, so what's happening? What about the future? How do we project what's going to happen in the next 100 years? A lot of the projections are based on global climate models, and if we take the Earth, the atmosphere and the ocean, and we write out the equations that govern flow in the atmosphere and ocean, the equations that govern interactions between radiation, the atmosphere, ocean, and land, we would have a set of equations that would not be solvable. So we can't just come up with an answer to those equations. And so what we do, like any of a number of these sorts of situations, is we come up with a numerical way of solving these equations, and that's a global climate model. We divide the world into boxes, and we solve equations that govern weather and climate on a discrete grid. So I'm sitting here in Wisconsin. I'm looking out my window right now, and the wind is from the north. So if I want to know what the temperature is going to be in the next several hours, what I may want to do is take a look at the grid box to the north of me. And if it's cold, then I might expect that the temperature is going to stay cold in the next few hours. And that's probably a pretty good bet. As we move into the future, so that's what these climate models do. They use those sorts of relationships, except based on equations that govern fluid flow and iterate the state of the climate system forward. So if we look into the future, we can take these climate models and we can force the climate models by expected changes in greenhouse gas concentrations. And of course, we don't know how our global society will evolve in the next 100 years. So what we do is we come up with storylines about what could occur. And here's an example of three of those storylines: the red, the green, and the blue lines on this chart here. So the red line, that's me attempting to use the arrow here. The red line at the top is what's referred to as the A2 scenario, and that's a scenario where people don't get along very well in the future. There's rapid population growth. There's not much sharing of information or technology, and there's very aggressive growth of greenhouse gases. And by the end of the century, then we see warming of about 3.5 degrees Celsius on a global scale. This blue scenario down here, the B1 scenario, is sort of the other end of the spectrum, where there's a lot of sharing of technology. Population growth peaks at 2050, and a much less greenhouse gas intensive economy. And then global temperatures peak at global temperatures at 2100 about 1.5 degrees Celsius, 2 degrees Celsius or thereabouts. Moving from the A2 to the B1 scenario requires some sort of global effort to change the way that greenhouse or fossil fuels are being used. And we refer to that as mitigation. Mitigation is necessary to avoid dangerous climate change. Now, I personally think the B1 scenario is very optimistic. Currently, our trajectory is above, in terms of greenhouse gas emissions, our trajectory is above every one of these scenarios. But it is possible that something will occur in the next 100 years. Even if we are able to mitigate down to a B1 scenario, there still will be a certain amount of warming that is inevitable. And so we're going to have to be able to adapt to the amount of warming that we will experience, even if we were to flip a light switch on the global economy right now, there would still be warming that is inevitable. So mitigation and adaptation are both going to be important as we move forward. What I'm going to be talking about today is the adaptation side of things, what we can do to try and identify how adaptation or how we can better adapt our natural and economic resources. Okay, so the example that I just gave here of about a 2-degree warming by the end of the century, or maybe 1.5-degree warming by mid-century. And incidentally, by mid-century, all of these scenarios are pretty close together. There's not much of a difference between them. So it doesn't really matter what scenario we're on in the next 50 years. Let me clarify. In the next 50 years, the warming doesn't really depend on what scenario. But what we do now has a huge effect on what will happen in the next century. So if we're looking at adaptation, though, the scenario is not as important. So I want to give an example here of moving from the global to the local scale here. So I was in my office a couple of years back, and I had a guy knock on my door and came in and said he worked for a company that made augers to drill into very thick lake ice. Now, keep in mind, we're in Wisconsin here, so those of you who are participating in the webinar from farther south, ice fishing is a big deal up here, as I've learned. And so his company builds these augers that drill into thick lake ice, and he walks in and he says, I need to know whether or not the last few years are going to be the norm for the future, because if they are, we have to change our business model. And this was a few years ago, and my response to him at the time was, well, global temperature is going to increase by 2 to 6 degrees Celsius over the next 100 years, right? And that means nothing to him at all. And it really means nothing to me either, because we don't live at the global scale. We live at a local scale, and we need to be able to interpret that information about global climate change at a local level. And so, by happenstance, a couple of years later, there was a number of scientists that got together with the Wisconsin Department of Natural Resources and the University of Wisconsin, as well as a number of other groups, and started asking this question: how do we assess what climate change means for us at a local level, and how do we develop adaptation strategies? And we put together the Wisconsin Initiative on Climate Change Impacts in 2007. The goal of WICCI is to assess and anticipate climate change impacts and to develop and recommend adaptation strategies. And one of the keys of WICCI is that we've put together WICCI as, I like to describe it as a conversation. It's a boundary organization that brings together scientists, policymakers, planners, across a wide variety of disciplines. And this is important because one thing that's very clear is that climate adaptation cannot be done in isolation. As a climate scientist, there's no way that I can know what's important to a particular impact, a particular system. I'm constantly surprised by, I talk to someone who says, oh yeah, for example, fish are sensitive to stream temperatures, and my assumption is that's due to the oxygen content of the stream, but no, it's due to the metabolic processes in the fish. And so there's no way I can know the breadth of impacts. So this conversation is really important. And one example of this some sort of estimate of how climate would change in Wisconsin. And at this time, Chris Kucharik, who's a professor in the agronomy department here, had developed a set of historical data for climate for Wisconsin that had shown that Wisconsin was warming. And we needed some information about how climate would change in the future. And so we submitted a proposal to the Wisconsin Focus on Energy program where we had outlined a methodology that we would use to produce estimates of climate change projections in Wisconsin. And in the meantime, these conversations were going on with WICCI, and we asked the people in WICCI what's important in climate information. And a number of things came back. There was a number of common threads. One, characterization of uncertainty was very important. And from a climate scientist point of view, my point of view, that's a big one for me. I want to make sure that we're thinking about the range of possibilities here. And uncertainty comes from a lot of different angles, from model physics, from emission scenarios, from the methodology of downscaling from a large to a small scale, and then other sources as well, things that we can't necessarily quantify. Another item that was identified was high spatial resolution, so 8-10-kilometer resolution, and daily time scale was something that people identified as being important because of the event-like behavior of some of these climate impacts. I'll give some examples in a bit. A third element that was important was the need to represent extreme events, so extreme precipitation, especially, and extreme temperatures for human health and for forestry and other impacts. And as we talked with the wide variety of scientists in WICCI, we began to realize that one of the most important characteristics of a downscaled data set would be its flexibility. Everyone has a different way that they need to use data, and too often we're constrained by the tools by the limitations of the tools that we have. And so the more flexible a data set is, the better off we would be in assessing climate impacts in the state. So this is an example of moving from a large scale to small scale here. One of the problems is that climate models have very coarse spatial resolution. So the plot on the left here is the typical resolution from some climate model, and you can see that Wisconsin is covered by 2 grid boxes, maybe. And that's not a particularly that's not particularly convincing. On the right is an example of that exact same data using our downscaling methodology, which I'll explain in a little bit. But it points out that in reality, things with climate varies, weather varies on a very small spatial scale, and sometimes these smaller scales are important. Whether they're important climatically or physically or not is sometimes irrelevant. Sometimes the small scale is important because people relate to information that's in their backyard. So even if the downscaling is just cosmetic, it's still useful because it allows people to engage with thinking about climate change. So there's a lot of reasons for downscaling, and the physical processes are just one. So I want to give an example here of there's a number of ways to downscale, and what happened was we got this the grant was funded. We started work on producing this downscaling data, we submitted the grant, we had all these conversations with different scientists, got all this information about what was needed, and we sat down on day one of trying to produce this climate data, and 20 minutes after we sat down, we realized that the methodology we had proposed would not address the needs of the people who were going to use it. And so we scrapped the entire plan at 20 minutes into the proposal. And here's an example of why the downscaling technique matters. So the upper left plot here is the average precipitation in July. And this is estimated from interpolating co-op station data, so observers who go out and measure precipitation and temperature every day. Interpolating that to a regular grid. And this is to do for historical data. It's the best thing you can do for estimating precipitation in between stations. And if you look at the upper right-hand panel, this is the fraction of wet days in that data set. And so what this tells you is if you want to go on a picnic in Wisconsin and you don't want to get wet, you should go find a co-op station and go on your picnic next to the co-op station, because the probability of being rained on at the station is lower than the probability anywhere around the station. And if we think about what's happening here, the probability of it raining at one station and not the other, if you have two stations next to each other, there will be days where it rains at one station but doesn't rain at the other station. If you're interpolating between the two stations, then it rains at every point in between those two stations. So interpolation tells you that it rains at every point between those two stations. And so you end up with an overestimate of the number of rainy days if you just interpolate. On the other hand, the bottom right shows the extreme events in Wisconsin. And what this shows is that if you don't want to get really wet, then the best place to go is far away from a station for your picnic. And again, we can use this idea for interpolation. The chance of getting a really strong rain event at one station and not another is pretty high. Rain is very, very localized. And so if you interpolate in between, it would be very rare to have an extreme event at two stations. And so anywhere in between then would be that the extremes would be muted. And so this methodology is not going to work because it violates what the users of the information told us was important, this need to represent extremes. So we developed a new methodology that's based on, that's a probabilistic methodology. And so instead of downscaling data itself, so downscaling rain to rain, what we do is we downscale the probability distribution that rain, and so I'm going to start talking about probability distributions here, and I'm looking at the number of attendees on the list here. And so just bear with me, it'll be about 2 slides here. I'm fully expecting that number to just start dropping off here in a second. If I see that go too fast, I'll stop I'll quickly move on to the results. Our methodology is based on downscaling the probability distribution of what could be occurring at the small scale, given that we know some information from the large scale. I'll give an example in 2 seconds here. The advantages of this is that the probability distribution is large scale, so it's more true to the existing data in the first place. We can retain the extreme events because we're interpolating this probability distribution around. And probably the most useful thing that actually we kind of realized as an after effect of this is that these probability distributions are incredibly flexible. It allows us to use this data in a really wide variety of applications. So let me give an example of what I mean by downscaling the probability distribution. So June 2008, the Lake Delton here in central Wisconsin flooded and washed out a man-made dam and a couple of houses just north of Madison here a little bit. And here's the precipitation over a 2-week period during that flood. A climate model would take an average over, say, 2 boxes over the state, and what it would say is that Wisconsin was wet during that time period. But if we look right in Lake Delton, in the center of this blob right here, there was 14 inches of rain in 2 days. If we look in southern Wisconsin, there was more like 6 inches of rain in 2 days. So a huge difference in over a small distance that both would be in the same climate model grid box. So what this tells us is that there's a distribution of what could be occurring at the small scale, even though the large scale tells us some information that it's wet. So given that the large scale tells us it's wet, there's a distribution of what could be occurring at the subgrid scale. And we quantify that distribution using a probability distribution. And that's the way that we do our downscaling. So here's an example of our other three panels show us some estimate of what could be occurring on that day, given the large-scale information that comes from the climate model. So that's the way that we produce this downscaled information. We're not actually predicting, of course, how much rain will fall on June 17th, 2047. But we are producing some sort of projection of the kind of rainfall that might occur in the future. The advantages of this methodology are here's some details of the data that we have. We use as many of the global climate models as we can find, as provides the data, the large-scale data that we need from the fourth assessment report. So there's 13 models that we use, and that provides some characterization of the range of uncertainty of physical processes, or the range of possible future projections based on physical processes. We use a number of emission scenarios as well. There are 3 different emission scenarios to give us some sort of range of future global emissions. The downscaling methodology resolves the range of probable climate change. As I said, this is essential for impact assessment. I'll give an example here. It also retains the extremes. Because we retain the probability distribution, we're not constrained by this interpolation. We interpolate the parameters of the distribution rather than the data itself. And so we retain the possibility of these extreme events. And then most importantly, these probability distributions are very flexible, so we can use the data in a number of ways. Let me give some examples here. How do we use this information? So the first example is a couple of examples of how we would use this, the range across model space of different possible climate changes in a risk assessment framework. So this is the spatial region that we've produced our downscaled data for. And a little historical note here. I'll see if I can use the line tool here. So when we started this, we were doing this for the Upper Michigan, or the Upper Midwest Great Lakes LCC, which there we go, which roughly falls in this area. And as we were doing this, and it extends a little farther south than that, but as we were doing this, we thought, well, as soon as we produce this data, there's going to be someone who's right across the border of this LCC who's going to want to use it. And it's kind of artificial to draw these boundaries to a certain extent. So we asked Brad Potter at the LCC and some of the other folks there, should we extend our domain? And they said, sure, why don't you extend the domain to the LCCs that intersect with the Fish and Wildlife Service Region 5. And when we did that, we ended up with a domain that looks something like this, this second circle. And when we realized that, we thought, well, this is ridiculous. We may as well just extend it out to the East Coast and extend it all the way to the Rockies, because as soon as we do this region, someone's going to come and say, well, can you just do the Mississippi River Basin? And that's exactly what happened. So we the entire eastern U.S. And what this shows is the mean temperature change for the region. So we see that over the region, I'll pick out Wisconsin because that's where I'm sitting, climate will warm by 5.5 to 6 degrees Celsius by mid-century, according to a middle-of-the-road A1B scenario. And I don't particularly like that because it's one number, and it doesn't give me any information about the range of our knowledge of that number. And so what I would prefer to look at is the range of possible warming, and we can quantify that using a probability distribution. So what I have plotted here is the range of climate change in mid-century as simulated by 13 of these 13 models. And what I've done is I've put this on probability distribution. So I would much rather say that Wisconsin will warm by 4 to 9 degrees Fahrenheit Fahrenheit by mid-21st century. And that 4 and the 9 are quantified numbers here. What it means is that the 4 and the 9 are the 10th and the 90th percentile. So what it means is that there's a 90% chance that temperature will, that warming, that the amount of warming we'll experience in Wisconsin will exceed 4 degrees Fahrenheit. On the other hand, there's also a 90% chance that it will not exceed 9 degrees Fahrenheit. And that upper number, there's uncertainty with those numbers as well, but that provides a range of possible future climate change. Now, this is useful because suppose you have a system that's susceptible to a 5-degree temperature change. In that case, we see let's see if I can move this arrow here. The 5-degree temperature change, there's about a 75% chance that the warming will exceed 5 degrees Fahrenheit in Wisconsin. So maybe you ought to consider coming up with some sort of adaptation strategy. On the other hand, what if you have a system that's susceptible to an 11-degree temperature change? In that case, there's only about a 5% chance that we'll exceed 11 degrees warming, and so maybe you don't need to worry about that system. By quantifying the range of possibilities, it allows us to start making decisions about what resources we're going to use. Maybe we don't devote resources towards understanding that 11-degree temperature change. Maybe we focus resources on areas that are more likely to that are more likely to have an impact. Also, maybe we don't worry about systems that are susceptible to a very small temperature change. Maybe we have to accept the fact that those systems are going to be gone, and we don't devote resources to those. So use a triage approach for some of those. That probability, the range of possibility provides us important information there. One thing we found is that warming is most pronounced in the wintertime, and this is consistent with most of the projections. Wisconsin, for example, is more like 5 to 11 degrees by mid-century, and this matters because in wintertime there's a number of Wisconsin is we're pretty proud of our winters up here. This is the Brook in the upper left-hand panel. And we can use this data, we can combine these mean temperature changes or this range of temperature changes in creative ways. So this is a plot of the probability that something falling from the sky will be frozen instead of rain. So the blue curve here is, this is for north central Wisconsin, so nearby where the Brook is held, not exactly there. And what it shows you is that in the middle of wintertime, if there's a precipitation event, there's about a 95% chance that precipitation falls as snow. With warming, this red curve is the projection for 2050. And what this shows is that by mid-century, there will only be about an 80% chance that precipitation event falls as snow. There's a 20% chance that if there's a precipitation event in the middle of January or February in north central Wisconsin, there's a 20% chance by mid-century that it will be rain, which is a huge difference from historical climate variations in that region. And that has a huge impact on the characteristics of snow in the area. So you can use these mean changes, these range of changes, to try and estimate other variables that are of importance to particular impacts, like the Brook and like the American martin here on the bottom left here, which is adapted. It's adapted towards snow. This is where the folks from the WICCI Wildlife Working Group would help me out a lot here, or they would glare at me for getting this wrong. But the American martin outcompetes other animals in the snow. That was a horrible attempt at explaining that, but that tells you why it's important that as a climate scientist I work with someone who knows something about the martin. Summer temperature change. Warming is least pronounced in the summer, and in Wisconsin it's more like 3 to 8 degrees Fahrenheit of warming. How do we use that information? That that matters a lot to brook trout. Brook trout are native to Wisconsin, and we can use that range of warming. So again, 3 to 8 degrees Fahrenheit here. There's our 3 and 8. That's our 10th and our 90th percentiles. We can use that in a risk assessment framework to try and look at brook trout habitat. And this is some work that was done at the Wisconsin Department of Natural Resources by Matt Mitro and John Lyons and some other scientists as well. Janice Stewart, I believe, was on this as well. In our current climate, the blue areas indicate streams that currently are habitable by brook trout. If we look at the low-end warming, about 1 degree Celsius, so that remember I said 3 to 8 degrees Fahrenheit, so about 1 degree Celsius of warming for the low end of that, 44% of the brook trout habitat in our state is gone. If we look at the mid-range of that, 3 degrees Celsius warming, 94% of the brook trout habitat in our state is gone. And if we go to the high end of that, the 5 degrees Celsius warming, 100% of the brook trout habitat in our state is gone. What this tells us, we can use this in a couple of different ways. And probably the most obvious way here is by motivating some sort of a triage effort here. There's no sense, even with a 44% loss, or with the 1 degree Celsius air temperature, brook trout habitat in the southwestern part of the state, and this just kills me to say because I'm an avid fly fisherman, but the brook trout habitat in the southwest part of the state is gone. So is it worth devoting resources towards trying to protect that habitat, trying to protect brook trout habitat in that region? That's a very controversial statement, and I'm looking forward to having someone blast me on that on the questions here. But maybe it makes more sense to try and think about these streams up in the northern part of the state where we can try and retain brook trout habitat. Another example here, using the probability distributions directly. So both of those previous examples were examples of how you use the mean change over a region or an area, and you use that with existing information to try and assess how climate may impact a particular system. Because we're doing probability distributions, we can characterize event-like behavior pretty well. The extreme events are pretty well characterized. And so what this shows is the change in the number of days per year that experience temperatures greater than 90 degrees on the left and greater than 100 degrees on the right. So we see that currently again, I'm going to use Madison as an example. You can tell I'm giving the talk. Currently we have about 6 days per year where temperatures get above 90 degrees. Now this year was an exception, but in general it's about 6 days per year. What this shows is that we should see an increase of about 20 to 25 days, so more like 26 to 31 days of temperatures that exceed 90 degrees during the summer. So that's a huge increase in the number of hot days. Similarly, we tend to get, by mid-century, we usually get about 1 day every 5 years where the temperature exceeds 100 degrees. I think we had 4 this year, but what this shows is that by mid-century, that's going to increase to 1 or 2 per year. And we can look across the whole country and look at how this changes. So here in Texas, we have an increase of 50 to 75 days per year, an increase. So 50 to 75 more days per year by mid-century that experience temperatures of 90 degrees or above, maximum temperatures of 90 degrees or above. And the 100-degree days, here's another month of days in Texas that experience 100 degrees or more. We can use that probability distribution to try and assess the impacts of extreme heat. Extreme heat has, and this is a picture from climatewisconsin.org. If you haven't been to this website, it's a fantastic website about just how climate change affects individuals. It's just there's some beautiful movies on there. So there's an example of a heat wave in Milwaukee. We can use this to assess extreme warm days and to quantify the changes in warm days. Extreme heat has, since 1982, extreme heat has killed more people in Wisconsin than every other natural phenomenon combined. So this is a huge impact of climate change. Extreme cold is also very important. This is we see that climate change means fewer cold days, and that's a good thing in general for heating bills and whatnot. But there's other impacts of that as well, and I'm especially thinking of invasive species, pests that are killed by cold days in the winter. And then a big one for us is forestry. In northern Wisconsin, there's a lot of wetland, and in the wintertime, the forestry industry relies on frozen ground to get in and harvest logs. Already, forest companies are building gravel roads in places where they've never had to build roads before. So already people are adapting to climate change in Wisconsin. And whether or not that's something that's a specific adaptation that they're thinking, oh, this is climate change, I'm going to adapt, or not, it's worth understanding how climate change is going to affect these practices that are already going on. Precipitation extremes. We can also use this data to look at extreme precipitation events. If you just count precipitation events, the nature of extreme events, because they're rare, there's a lot of error in estimating the extreme precipitation. And so using the probability distribution directly to estimate extreme events is a much more robust methodology for looking at changes. And so I'm going to just skip through here. Here's the change in the number of 2-inch rainfalls days per decade in the data set here. And so you see in general about 5 to 8 more rainfall events of greater than 2 inches per decade and along the East Coast here. In the West, where it doesn't rain as much, or where you don't get those big events as much, there isn't as much of an increase. And similarly, 4-inch rainfall events, we're seeing probably the effect of tropical cyclones in the data, or extreme precipitation events associated with flow off the Gulf. So increase in extreme precipitation events expected. And we can get this from the probability distributions, a much more robust estimate than by just counting events. A third example, spatiotemporal data. So this is an example I showed earlier. And what we do is with our downscaled data, we have some estimate from the large scale model, and we produce some sort of a realization of what could be occurring on the small scale. Now, there's more information in this panel on the upper right than there is in the panel on the upper left. So we've somehow created information here. And what we do is we add in a spatially coherent random distribution of precipitation that we apply an advective diffusive equation to allow this sort of streakiness, to allow the fact that precipitation systems, once they develop, tend to propagate with the wind. And so we use the mean of the wind on the model's producing to advect those sort of random numbers around. And so these three realizations here are equally probable realizations of what could be occurring given the large-scale variation, large-scale rainfall in this upper left map. The advantage of this is that if you have say a forest model that you're forcing with temperature or precipitation data, and that forest model is susceptible to like fire or extreme events or event-like behavior, we have a number of realizations that we can produce so that the extreme events are well characterized, or better characterized than just a finite 20-year sample. And so we've made sure to have several realizations from each model simulation. Here's one example of using that data. This is from a previous version of the downscaled data, but we're going to be doing the same thing for this downscaled data for producing estimates of snow characteristics in Wisconsin. You can use the precipitation and temperature data to drive an offline model. Snowfall, forestry are examples of that. Another, we've ensured that the temporal variability in the data, the day-to-day variations at any individual point are realistically characterized. And so what that means is that we can do things like assessing duration of heat waves. This black curve in the bottom here, this is over central Wisconsin again, so this black curve is the number of heat waves of duration heat wave, meaning 5 days in a row above 90 degrees Fahrenheit, occurs once every 20 years. It's very rare. By mid-century, that's more like 6 times every 20 years. So about once every 3 years. This has a huge impact on human health. We can do this because we've ensured that the temporal variability in the model is realistically portrayed. The last example I'm going to give here before I realize I'm going late here is one that I think is a really exciting use of the probability distributions, and that's rescaling existing data. So here's an example of that. We're doing this for the Milwaukee working group. Sandra McClellan and some other researchers are looking at the combined sewage overflow of the Milwaukee sewerage district. And they have a model of the Milwaukee sewer system that they force with historical precipitation and historical climate, the sequence of climatic events. It's really expensive to run that model. And because combined sewage overflows are event-like behavior, events, instead of running some random realization through their hydrological model, it makes more sense to take the historical data and say, what would this data look like if these rainfall events, this exact sequence of events, occurred in 2050 instead of 1980? And so we can take, because we have the probability distributions, we can take an existing time series and rescale it. So here, as an example, here's suppose we had a day that was 13 degrees Celsius. That day would be the median for the historical record for June there. That day scales to 16 degrees Celsius in the future. The advantage of this is that we retain the exact sequence of events of what occurred in the past, only under future scenarios. So what you can do is you can investigate the policy response to a specific synoptic event and say, how would we have to adjust our policy response if that event had occurred under future conditions? So it allows, it's just a very different way of using the data. But because we're doing all of this using probability distributions, it's very simple to do that. This is an example of rainfall. This was a flooding event in Madison here, mid-August 1987. And the GFDL, this particular model, has August becoming a lot drier. Precipitation variations in our region are somewhat uncertain, and I don't think I have a plot of I think it did not include the plot of mean precipitation change. But in general, the north gets wetter, south gets drier, and Wisconsin's right on that nodal line in between, so it's hard to know what's going to happen here. Here's an example of that event-like behavior. This is a combined sewage overflow, a photo from the Senator McClellan provided, and this gray, or this brown here is the sewer system overflowing into Lake Michigan. I was told that the intake valve for the water for Milwaukee was somewhere around here at some point, and I'm sure I had that wrong. But after a few of these events, they decided to move the intake valve. Senator would have the official word on that. So I want to conclude here by a couple of statements here. WICCI, in partnership with the Upper Midwest Great Lakes Landscape Conservation Cooperative, has just produced a new set of downscaled climate data for use in climate impact assessment. And the data is what I've shown today is a preliminary look at that data. It is available if you're ready to use it. It is available. Right now, the easiest way to get it is to mail us a hard drive, and we can put the data onto that hard drive and mail it back to you. I don't think that's a particularly great way of using the data, serving the data. So we're looking to, we will be continuing to work with the Upper Midwest Great Lake LCC to provide a better, a more user-friendly way of getting that data. One of the keys here is the downscaling methodology was developed based on conversations with the eventual users of the data. Before developing the methodology, we talked with people who were going to use it to make sure that the methodology we use would be useful to them. And I really want to emphasize that in climate impact assessment, that this conversation is essential. We can't, as a climate scientist, there's no way I can know what what's going to be useful. We use a probabilistic framework, which allows us to characterize the range of possibilities. As a result, the extreme events are well characterized, and most importantly, the data are very flexible, and I gave some examples of that. Last, we have additional efforts to work with the LCCs to develop a more user-friendly interface to serve the data, and I'm hoping in about 6 months or so, the next 3 to 6 months, we'll have a web-based server, a lot like the USGS server. If you've seen this, I don't have the climate data portal. I could be wrong on the name of that. Where you can upload a shape file and get statistics for a particular region. I'm hoping that we'll be able to develop, work with them as well to develop something like that. We are developing a mechanism in WICCI to provide more specific expertise and interaction with users. If you just want the data, you can mail it to a hard drive, put the data on the hard drive, and ship it to you. But oftentimes, it helps to have conversations and think about how we can use this data to better tailor it to a specific project. And we're developing a mechanism to provide a lot more of that service to people who need to use this. And I think the LCCs are really useful in that sense in providing a network to do this. We're also downscaling new variables. We have a graduate student, Megan Kirkmeyer, who's completing a project on downscaling wind in the upper Midwest. We'll have snow characteristics pretty soon, and estimates of evapotranspiration. Evapotranspiration is one that a lot of people have identified as important. And once we have wind, temperature, rainfall, we might have a couple of different methodologies for getting evapotranspiration. And then finally, the next generation, this is sort of the long term, will include the CMIP5 models. There's a lot more models. There's a lot more data stored, so we can do a lot more. We have ideas for better treatment of fine-scale orography. If you have specific impacts in the Appalachians or in the Rocky Mountains, we have ideas of how we can come up with some good estimates of climate variations in those fine-scale topography. And we'll probably extend it to the entire U.S. at that point. So if anybody wants to fund that, feel free to give me a call. I'd be more than happy to talk about that. So that's where I'd like to end it. And I'm sorry I went over. But there's 3 different websites I put up here. One is the WICCI website, wiki.wisc.edu. Second one, I provided a number of images from climatewisconsin.org. If you haven't seen those videos yet, they're just they're very effective at just engaging people and understanding how climate change affects people. And then, of course, the Upper Midwest Great Lakes LCC, which funded the research and who we're working with to provide more interaction with people. So I'll leave it at that and take questions.
Okay, thank you. Are you okay if it's about 58, or about 2 till, so if we extend to maybe 5 after or so to get a few...
Oh, yeah.
Okay.
Yeah, I am. I'm sorry for going long, everyone.
No, you're fine. You're fine. And actually, a lot of the questions were answered right towards the end anyway, dealing specifically with how they can get this information. One question in particular, people were asking, you had mentioned that people can get information by sending a hard drive. Is there an address they should send it to, or is that on the WICCI site?
What we'll do is at this point, we'll have you send an email to either myself or Carolyn Betts. And Carolyn perhaps can, I know she's on the call right now, she might be able to, maybe what I can do is we'll have some sort of a statement on the WICCI website, and then I'll also talk with Brad Potter at the Upper Midwest Great Lakes LCC and ensure that there's some sort of contact information there, so that you can go to either of these, the top or the bottom website that's posted right on the page now, and find out contact information about how to do that.
It's 13 hours.
Okay. Well, let's do a few questions, and then whatever questions he isn't able to answer today, we'll post later on the website with his answers. So there were several questions that people were asking specifically with, are other states doing this type of research where they could get, they wanted to know if this the research that you have, the downscaling models that you have, are specifically only for the Great Lakes states, or is it something that can be that goes broader?
Yeah, that's a good question. So initially we were thinking our initial efforts were just for the Great Lakes states and for Wisconsin, but once we started talking with the LCCs and with the Fish and Wildlife folks, we recognized that there would be a lot of people who would be interested in using a consistent data set. People comparing results, people doing efforts across boundaries and so forth. And so we did a lot to try and ensure that this methodology is generally applicable anywhere in the region that we have posted. And those maps that I showed earlier are the region that we currently have. It extends into Canada, all the way the eastern half of the U.S. I think the data in the Appalachians is probably pretty good. We do use a prism-based methodology to do interpolation in topographic regions and near coastlines. So the data does include things like lake effect. It does include elevation and aspect ratio adjustments to precipitation in mountainous terrain. We did not extend into the Rockies because that was sufficiently different that it would have required a lot more of an effort. But the next data set that we use, if you're in Colorado, you might contact some of the local people there. I think there's some efforts through NOAA as well as other places for downscaled data in really mountainous terrain there. But I think, yeah, it's very applicable across the entire eastern U.S. and I'd be very curious to. We've done a lot of evaluation in Wisconsin, obviously, of the methodology, and I'd be very curious to get some feedback from individuals as to how it does and how useful it is for them in the Appalachians and other regions.
Okay. Just a follow-up question dealing with the new downscaled data. Is it reflected in the Climate Working Group's interactive maps on the WICCI website?
It is not yet, no.
Okay.
We will. That's one thing we'd like to update.
We had a question dealing with the information of how it is distributed. One person specifically asked about, has this information been presented to, say, like county extension agents or state and federal wildlife land managers? Yeah. And if it has, how and what has been their reaction to how they can use it?
Yeah, it definitely has been. We've worked directly with a number of different groups to try and help that process out. I think in general it's well received. I mean, probably the best people to ask would be. I'm afraid I'm going to run out of batteries here soon. So it has been pretty well received, I think, but. Yeah, we are definitely working with people already with the previous version of the data and with the current version of the data.
Okay, let me do one more question, and
I'll just say I'm happy to stay on as long as possible. My phone is beeping at me here, so.
Okay. Well, actually, maybe what I'll do is I'll end it now, so that therefore we won't get you cut off, and. We'll just get the questions to you, if you don't mind answering. Some of them are specific to some slides, so I think there was a little bit of time to actually go back to those slides. So if you're okay with that, that would be great.
Yeah, that's fine. That's fine. I mean, I can also just stick on until it cuts off, so whatever works out.
Okay. Well, let me just ask one more question. Someone asked, sorry, I'm trying to...
While you're going through that, while you're looking for that, let me just say thanks to everyone who did attend, and if you do have questions, please visit these websites, and we'll put up contact information. Please do feel free to contact us through WICCI. Carolyn Betts is the contact through WICCI. If you have questions about WICCI or about the data, you can get in touch with us as well.
Okay. One last question. Has anyone evaluated how non-scientists interpret probability distributions like the one shown for temperature?
Yeah. That's a very good question. We have an outreach committee here that is outreach and communications committee that works very much, that is thinking very much about the audience and how people interpret this. And I've presented this on a scientific level to people who I assume most people at a level that might be different than I would present to other audiences. So yeah, WICCI is thinking very much about the social side of this and how people perceive information and how people use that information as well. That's probably one of the most important things about climate impact assessment is is assessing how people are using the information, because that informs how we present the information, what research we do, what unknowns there are, and so forth. And WICCI is very much organized to address these kinds of issues.
Okay, great. Well, let me just close now. We'll get the answers to the rest of the questions within the next couple of weeks up on the website, along with the archived webinar from his talk. I wanted to again thank you, Dr. Weimant, for your willingness to talk with us today about your climate research. An excellent discussion. Also, a thank you to NOAA, the Upper Midwest Great Lakes Landscape Conservation Cooperative, the National Sea Grant College Program, for funding this webinar. I did want to remind you that our survey URL for this webinar is in the chat feature. Please take a few minutes to fill that out. We would like your input as we develop a regional climate website, so please take the time if you could. I also wanted to refer you to resources in the archive of all previous webinars presentations, which are located on our changingclimate.osu.edu website. This webinar series is sponsored by the OSU Climate Change Outreach Team and will continue next month with a presentation by Dr. Lonnie Thompson of The Ohio State University, who will be discussing climate change and his extensive work with ice cores. Thank you again to Dr. Weimant and all the participants on this webinar. We hope this was beneficial and hope you'll join us again in an upcoming webinar. Thank you and have a great afternoon.
Thanks a lot.